Hello folks, today I'll go over the exponential growth and decay models. But before that we have a basic model which is called the it's good to start from here, uninhibited um, uninhibited population growth model. So in this model you have no restriction on the population. So this model is given by dp over dt equals k times p. But if you observe, you can just see p prime of t is a constant multiple of the actual function p. So this model directly implies, and it's used heavily in many areas in business when we talk about compound interest formulas, when compound like interest is compounded continuously. This model directly gives us the exponential model. So the solution to this differential equation is p of t equals the initial value p0 e to the power k times t. So this p0 is our initial value. And this model is what we call the exponential growth or decay model, depending on this k. So here k, we think of this k being the rate and p0 being the initial value. So this directly produces the exponential model p0 e to the kt. And we can clearly check this over an example. I mean, take a look at this example. Let's say, for example, you have f of x equals e to the 4x. Now let's say like 3 times e to the 4x. If you look at f prime of x, that's going to be 3 times e to the 4x multiplied by 4. So you see that produces a 4 compared to the actual function. So you can see this f prime of x becomes 4 times f of x. So it's exactly of this format, that the rate of change is a multiple of the actual function. That means this is an exponential model, and you can clearly see that. So whenever we come up with a problem like this in which the rate of change is a constant multiple of the actual function, then that means we're talking about the exponential growth or exponential decay. But the model will be usually given in the problems, so it's going to be straightforward that when you see this model, we're talking about the exponential growth or decay. So like there might be some like basic examples, like one basic example. If you're, for example, talking about the equation dA over, let's say, dx equals 5 times a, see, the rate of change of a is a multiple of the actual function, so that produces the solution a of x equals a constant c times e to the power 5x. So that constant c is the actual initial value. Or let's say you have dp over dt given to be negative 0.4 times p. That means this p of t now is a constant c times e to the power negative 0.4 times t. So you see these type of models every time produce an exponential model, exponential growth or decay. This is a decay because k is negative, here k is positive, so it's a growth. And we will see that better on different examples. So here's the first example. Let's say assume that example as p0 dollars is invested, and it's invested in an account in which the interest is just compounded continuously at the rate of 7%. So from here you can just see the equation given for this is dp over dt equals that 7% times p. This is how the balance is growing. This is this is the rate of the balance. So it's like you can just see balance growing. So the first problem, part A, it says, can we write down the function, actually, which is kind of like the solution to this differential equation. That's the first part. So you see the rate is given. This model is an exponential model. So we have this P of t is equal to P0, the initial value, e to the power 0.07 times t. So this is the model given. And then this is the function, right? So in part B, it says if $10,000 is invested, what's the balance? What's the balance after a year? So how do we find the balance after a year? It's simple. P0, this is P0, the initial value, and then this is time, t in years. So P of 1 is what we're looking for. So that's going to be 10,000 e to the power 0.07 times 1. This is what we will get, and this is going to be $10,725.08. So that's what we got. And then we have one more part for this problem. It says part C, and that says if still like you invest 10,000, how fast is the balance growing? At year 1. So this is the question, and in here you see how fast is the balance growing. So you're talking about rate of change. So in this case, what you will do is you will find the derivative of the function. So we have p prime of t. That's going to be, we keep that 10,000, that's the initial value, and e to the power 0.07 times t multiplied by 0.07. So that's what we get from the chain rule. See, like here we got this because of the chain rule. So in this case, if you just multiply those two numbers, it's going to be 700 e to the power 0.07 times t. This is p prime, the rate of change, and they ask us to find p prime 1. It's going to be 700 e to the power 0.07 times 1, which is going to be 750.76. So this is the rate at which the balance is growing. Balance is growing, and this is of course like you see that dollars per year. This is the rate at which the balance is growing at year 1. After year 1. Here's another example. It says the world population is given to be 6.04 billion at 2000. So and the population is growing exponentially at the rate of 0.016, or just we can just say 1.6%. And the model given for this is, you see this is dp over dt equals 0.016 times p. This is the model given. Of course, this one is the rate. It's like per year. You need to put that one in there. It's just per year. And this is time. T is in years. So T is the time in years after 2000. So this is all just given in the problem. Now the first thing is this. What's the equation? What's the function? Part A. What's the function for this model? It's an exponential model. Actually, you can see that when it says growing exponentially. So which means the function P of t will be 6.04 e to the power 0.016 multiplied by t. This is the model. And then part B says, can we find the population at 2020? That's the question. So you see this one really implements just t needs to be 20 in the function p, so we will find p of 20. That's going to be 6.04 e to the power 0.016 multiplied by 20, and that's going to give us 8.32 billion. That's the population. And part C, one more question. It says find the rate of change. Find the rate of change of the population at 2020. So here you see when it says rate of change of the population, you need to find the derivative. So we take a look at p prime of t. It's clear. You just take the derivative 6.04 e to the power 0.016 times t from chain rule, multiplied by the derivative of top, which is 0.016. Okay, and if you simplify, that's going to be 0.09664 e to the power 0.016 times t. So this is p prime. And at 2020, it's just 20, so we will look for p prime of 20. We plug in 20 in the derivative function, so it's going to be 0.09664 e to the power 0.016 multiplied by 20, and that's going to give us 0.133 billion people per year. So that's the rate of change, or just you can say move 3 decimals to the right, so it's like 133 million people. This is the growth rate. So it's kind of like this is the rate at which population is growing at 2020. So this is how we find that problem. So it's pretty much straightforward. You first write down the model, next you just calculate that value of the function at some given value, and then you find the rate of change. They're all like typical type of problems. Next, if we discuss a little bit about exponential decay, it's just a similar format, but you got this time the model with a negative rate, negative k times p. And so the model p of t will be at initial value p0 e to the power negative k times t. This is when we have the decay. And the difference between the growth and the decay is that if you look at the exponential growth function, you have the initial value here, let's say p0, and the function is increasing. And this is when you have the growth. For the decay though, you have the initial value, but this time function is simply going down. It's decreasing, a model of this type. This is when you have the decay. We have a lot of applications of this decay in chemistry. Amount of some sort of elements can go down, that can decrease. We have that type of examples. And we have a rule for finding the half-life of an element, of any substance. And this half-life for the decay, of course, like half-life, we can only talk about that with the decay. Half-life, T is given by ln2 over K for a decay model. So just a simple example. Let's say you have, let's say we have an example. We have an example. It's kind of like, let's say you have plutonium 239. It has a decay rate. It is a decay rate of 0.0028% per year. So if you try to figure out the half-life of this element, it's going to be T equals ln2 divided by K. So it's going to be ln2 divided by 0.000028. You convert that percentage into decimal, and it's going to be 24,755 years. So that's how you find the half-life. One final example about exponential growth and decay is finding the present value of an account. So for example, let's say you want to save for a child's 20th birthday. Let's say you want to save $10,000, and the account is just in the account, it's compounded continuously, and the rate is given to be 4%. So see, this value 10,000 is the feature value of this account. So you want to find the initial value, and this is an exponential growth problem, but be careful, this is the feature value. You want to find the initial value of the account. So what's the initial deposit that you need to make to get 10,000 after 20 years? So it's really simple, but now you're going in the reverse direction. So we have P equals P0 e to the KT, because this is the growth count, and now the feature value is given to be 10,000, and the initial value is not given. E to the power is 0.04 multiplied by 20, because that's the number of years. So this 20th birthday, that means number of years is just 20 in this case. So this part will be, you will see that's e to the 0.8. So you divide both sides by e to the 0.8, so the P0 initial value will be 10,000 divided by e to the 0.8. This is how you solve such a problem. So that will give you the initial value. So initially, we got $4,493 $12.29. This should be the initial deposit, so that within 20 years you will be saving 10,000 in this account. So this is kind of like that overview about the exponential growth and decay. Hopefully that's gonna be helpful. Thanks for watching. Bye.